off. So this is where we left off. We were drawing equipotential lines at two charges. And then here is kind of the summary of that, okay? So we're mentioning that the equipotential lines have to absolutely be perpendicular to the electric field lines. And that we can determine this experimentally. High potential closest to the positive, low potential closest to the negative. All right, so here we have the opposite situation where we start this time with an equipotential map of two charges. And based on those two charges, we can figure out what's going on with the electric field line. So we should be able to work backwards, which is what you guys are essentially going to be doing on the lab. So if I were to start an electric field line from the dot that I just drew on the left, I would have to, if I were going towards the right, I would have to pass and go through perpendicularly through all those equipotential lines. And that's how I know there's an electric field line there, right? It's perpendicular to those lines. If I were to go a little bit more upwards, it would go up perpendicular to this one, perpendicular to this one, but now I'd have to curve it around a little bit to get perpendicular to that other one. I want you guys to practice that just now, okay? If you guys have a touch screen, do it on your touch screen. If you guys have a piece of paper, just recopy it, like roughly what that is, and try to get into the practice of drawing those equipotential lines. For sure, that is something that you guys are going to need to do for me. If not on a lab, then definitely on a test. And remember, electric field lines can never ever cross. Did you say it's a Ninja Turtle? How bad was that Michael Bay Ninja Turtle movie? Oh my god. That's bad. Don't watch it. And don't forget, electric field is a vector, so your lines, your electric field lines should all have arrows. All right, in this case, they're negative charge, so they're all going towards those negative charges. Okay. If I didn't know that those charges were negative, how else could I determine that those were negative charges? What piece of evidence was on that picture on the left that might indicate that those are negative charges? Gabriella? Yeah, absolutely. The fact that there is a low potential, a very low potential in the middle of those, and that the potential is increasing but in a negative direction, means that there's a negative charge there. If you guys go to oh, actually, we'll wait a couple seconds. So if we move on, we can determine that the equipotential lines for a point charge, kind of like what we drew in 2D, but if you had to imagine in 3D, it would be like there would be a point charge in the middle, and there would be these equipotential spheres or hollow spheres all around it, all right? And all along that sphere of radius r, right, there's going to be the same voltage, and therefore you have this equipotential like cloud that surrounds this proton in this case, right? And if you go out further, then it's the same thing. It's just now you have a lower voltage. So if I were to compare points A, B, and C, what would you say about them? What would you say about points A, B, and C? What? Same voltage. What would you say about points A and D? Who's higher? Zach. D is a bigger voltage. All right? If this was an atom, and this was the nucleus of the atom, and these are the electron clouds, if an electron jumps from this cloud to this cloud, is it going to a higher energy state or a lower energy state? Eh? Higher energy? So remember, in a nucleus, the inside is what? What's the charge of the nucleus? It's always positive, okay? If there's just protons and neutrons, and the neutrons don't contribute to the charge, and electrons are positive or negative. So is it going to be lower energy when it's closer or higher energy when it's closer? Eh? Higher? Does the electron want to be close to the proton or does it not want to be? It does not want to be, but the forces are going in that direction. Opposites attract. So remember my drawing of a big positively charged object, and it goes down to here. Which one is going to have more potential energy? More potential energy or more potential energy at the bottom? More potential energy here. So this is actually a high energy state, and this is a low energy state. So it's going to want to go to a low energy state. So electrons, when they lose energy, they go down to the lower shell. However, if there's already 2 electrons on that, as you guys know in the sp, ef orbitals, you guys learned those? On that smallest orbital shell, there can only fit 2 electrons. So if there's already full, because there's electrostatic repulsion from this electron, then there's a very low likelihood that you have an electron jumping down into that. But if that shell was empty, that electron is for sure going there, because that's definitely the lowest energy state. What class did you guys learn that in? Chem or organic? Chem? Is that Chem 1? Or what's it called? Gen Chem? All right. We also talk about parallel plates, and the equipotential surface of a parallel plate is a surface, right? So everywhere along this blue square is going to have the same potential, so therefore it's an equipotential surface in this case, right? It's no longer a line, it's in 2 dimensions, and this one is also going to be an equipotential surface. If I were to ask you, which one of these has which one of the plates has a higher voltage? This one or this one? The plus one or the minus one? Which one has a higher voltage? The what? Which plate has a higher voltage? The negative or the positive? Let's go back. Is it here? I just circled the sentence. This sentence is what you need right now. Okay? It's not the sentence you deserve, but the sentence that you need. You know what I'm referring to? No one? So, was that? You got the reference? Okay. It's from Batman, guys. Come on. All right. So what is it? Which one is a higher voltage? Zach? Positive. High voltage. Low voltage. And so between these two surfaces, which one's going to have a higher voltage and which one's going to have a lower voltage? This one's going to have a higher voltage, yeah. I would just call this V1, V2, and V1 is greater than V2. Yeah. Here's another practice. Try to reproduce it in your notes or do it on the screen in front of you. It's a drawing the electric field lines. So these are equipotential lines. Try to draw them. I mean, we'll try to do this quick, but try to draw them on A, B, and C. And if you're just feeling bored or whatever, try to do more of them. But try to do the electric field lines that pass through A, the electric field lines that pass through B, and the electric field lines that pass through C. Hence, they're not all the same lines. You're going to have to draw 3 different lines. So remember, your electric field lines are going to go perpendicular to the equipotential lines. Okay? So if I were to draw the most simple one, there would be a line that kind of passes through like that. What's that? Got it. I'm just going to print something and we're going to work on it a little bit. So hang there. I'm just going to I'll be right back. All right. So hopefully, yeah. When they come closer to the nucleus, they have a lower potential energy or a lower potential. They have a lower potential energy because the electron has a charge, and it's going to an area of lower potential. You get it? Isn't a very confident yes? Well, process it and then ask me if it still doesn't make sense. Hopefully, okay, actually, before I draw anything on this, if there were charges here, what would the charge be around over there, where I drew that circle? Positive or negative, or we have no idea? You think it's positive? Anyone else? I agree. I think it's positive. Where else would you find a charge here? Top left? What kind of charge would you call that? Yeah, probably negative, right? We're all assuming that this is just point charges, but we don't actually know. Is there another one that we can tell? Well, let's draw the electric field lines and see what we get, okay? So if this, I drew one already, could you show me which direction the arrow is going? Is the arrow going towards the left, or is the arrow going towards the right on the electric field line that I drew? Left or right? Left, yeah, very good. It's going from positive to an area that's less positive. Okay, now I have to draw lines that are perpendicular to all of these, so I'd go do something like this, like this, like this, like this. So look where all those electric field lines are going. So what's going to be down here? Yeah, negative charges. The same thing up here. So you should have something that looks like that. All right. That's gorgeous. Thank you. I did work very hard at it. Here's a question for you guys. So a proton is released from rest at point Q, where the potential is 0. What does the proton do? Does it stay there? Does it move to the left? Does it move to the right? Does it change speed? Does it not change speed? What's going to happen? So someone tell me what you got. Does it first of all move to the left, or first of all does it move to the right? To there? It moves to the right. Is that right? How did you get that? It's going to go towards the left. All right? Because it's positive, it's going to go towards the negative potential, because the negative potential is where there is less protons. And is it going to go at a constant speed, or is it going to increase its speed? Increase its speed, exactly, because there's a force. If there's a force, therefore there's an acceleration. There's acceleration, it's changing its speed. So the answer would be C. Here's another one. Rank in order from largest to smallest the potential differences from 1 to 2, 1 to 3, and 2 to 3. Let's do V12 first. Yeah. So you need to find out if it's, you gotta go increasing, right? So you're gonna find the negative ones, and then the ones that are 0, and then the ones that are positive. So that's what our job is right now, is to figure out which ones are gonna be positive, which ones are gonna be negative, which ones are gonna be 0. Okay? There is one that has a potential difference of 0. That means they're equipotential. Which one would they be? 1, 2, yeah, very good. So this one's going to be 0 volts because they're on the same distance from charge Q. Therefore, their potential is the same, and therefore the potential difference is 0. Is 3 at a point that is lower potential or higher potential? Lower, very good. Thank you for responding and making me feel important. And if it's going from, because the delta says 1, 3, so we're talking about delta V1, 3. If it's going from 1 to 3, is it decreasing or is it increasing its potential? It's what? If it's going from 1 to 3, is the potential increasing or decreasing? It's decreasing, so the delta is going to be negative, right? And it's decreasing from a difference of r. I'm going to call that distance r. It's going to decrease that distance because remember, it's all radial. Yeah. Exactly. Yeah. We're not talking about electrons here, though, so this is the opposite of what we were talking about before. These are test charges, which are positive. And what about the difference between 2 and 3? If 2 were to go to 3, is it decreasing or increasing its potential? It's also good. And it's decreasing again by the same radius r. So in fact, you can say that these two are equal. And if we had to order them, then it would be delta V1, 3 is equal to delta V2, 3, which is less than delta V1, 2. Okay? All right. Yeah, sure. Yeah, sure. The test charge? Yeah, it's positive. Yeah. It would be the opposite. Yeah. Oh, no, 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 sorry. You're talking about the voltage, the order of the voltage? No, the order of the voltage is always the same. Okay? It's the energies that will be different if you add an electron. If you caught the positive, if you put the test charge as an electron. Irrespective of what I'm changing, right? But the energy would be respective of the charge that I'm moving up and down. Right. When you have a charge and you let go of it, it's going to move in a certain direction. So it has a potential energy, and that potential energy becomes what? Becomes kinetic energy, and vice versa. If you take a moving charge and you stop it, where does that kinetic energy go? Goes into what? What's that? Potential energy, exactly. So here is an example of that. You have a proton traveling at 800,000 meters per second, right? And it's got, what kind of energy does it have if it has the velocity? As what? Kinetic energy. And it comes to rest. So therefore it loses all of its kinetic energy. And all of that kinetic energy in an ideal world becomes what? Potential energy. It's like throwing an object upwards. You have the initial kinetic energy that's slowly decreasing, reaches a peak where it doesn't have a velocity anymore and it only has potential energy, and then it falls back down. So this is the exact same situation. You have this proton that has kinetic energy, is being launched towards something that's definitely going to be of what charge? Positive or negative? If it's slowing down and coming to a stop, it's getting launched towards that positive, exactly. Because if it were negative, it would just get attracted to it all the way until the end. So it's a positive, it's getting shot towards a positive energy source, a positive charge source, and it's going to slow down to a stop. Now, all of that energy gets converted to potential energy. So 1/2 mv squared is going to become its potential energy, and its potential energy is kq1 q2 over r. This is me saying the kinetic energy is becoming potential energy. Did this proton go into a region of high potential or low potential? Remember, this is something that's getting launched towards a positive charge. Yeah, what do you think? What's that? High potential, absolutely. Right? It's entering a region of high potential. And if you guys remember, it's energy or potential energy per charge is equal to the voltage or the volt. I won't put delta, I'm just going to put volt. It's high energy, it's potential energy per charge that gives you voltage. So if I calculate the potential energy here, right, because all my kinetic energy is getting converted to potential energy, and if I have the potential energy and if I have the charge of the proton, I can easily find the voltage. So could you guys do that, please? First, find the kinetic energy. Assume that all that energy was converted to potential energy, and then find the amount of energy per charge to determine what the voltage is. Is that going to give you a really small number or a really big number? Small. Someone have a number for me for the kinetic energy? What would the units be? joules? 16 joules. Okay, good. If that's my energy, and all that was converted to potential energy, my potential energy divided by charge is going to give me my voltage. So it's going to be 5.34 times 10 to the minus 16 joules over Q, which is 1.6 times 10 to the negative 19 coulombs. You have a number? That sounds about right. Volts or joules per coulomb. All right. Not too bad, right? Okay, let's do another example. A proton speed is, as it passes point A, is 500 meters per second, as it follows the trajectory shown in the diagram. What is the proton speed at point B? First of all, is it going to slow down or speed up, according to you? Going to speed up? I agree with that. I agree it's going to speed up because it's going into an area of low potential. So it had a delta V of 40 volts. So how much kinetic energy did it gain? How would you calculate the amount of kinetic energy it gains? Would it be equal to the amount of potential energy lost? It's a rhetorical question. Yes. All right. The kinetic energy gained is the amount of potential energy lost. So let's figure out how much potential energy was lost. Well, that's delta V times Q. How much potential energy did it lose? (6.4 times 10 to the minus 18 units? Potential energy is in joules. Very good. So if it lost that much potential energy, that means it gained that much kinetic energy. So let's solve for velocity. So again, the potential energy that I lost is going to be used to gain kinetic energy, and that kinetic energy gets converted to a velocity. That's little v for velocity, not voltage. Did somebody get a number for that? Elizabeth, yes, something? And the square root? Yeah, everything has to be. 8, 7, 5, 4, 8 meters per second. Can someone confirm or reject that number? You got it? You got it? Okay, good. So now, is this the final velocity of it, or is this the delta velocity of it? Is the what? That's the delta. That's how much velocity it gained. So you actually have to add the initial velocity to it to find out what its final velocity was, right? So that's going to be 137,548 meters per second. Because I want to know what the final velocity was, not how much velocity it gained. You guys understand why I did that? If it's not clear, don't be shy to ask. I'm going to stop here. I'm going to ask you guys to do a little exercise. It's going to be in preparation for the lab. I'll give you guys 20 minutes. I'll collect it at the end of class and see what you guys have done. You guys can work in pairs. Everyone's